warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. We are delighted to welcome all of you to Universitas Sebelas Maret and to this conference. I am Suci Faniandari, will be the host for today's event. We are also delighted to welcome the Honorable Professor Ahmad Yunus as Vice Rector of Academic Affairs, Universitas Sebelas Maret. Good morning, Prof. The Honorable Dr. Harjana as Dean of Faculty of Mathematics and Natural Science, Universitas Sebelas Maret. The Honorable Professor Budi Purnama as Chairman of the International Conference on Science and Applied Science 2021 as well.
Good morning.
And to the Honorable our keynote speakers, Professor Andrivo Rusdi from Physics Department, National University, Singapore. Professor Satoru Yoshimura from Research Center of Advanced Material for Breakthrough Technology, Akita University, Japan. Dr. Isao Watanabe from Mason Science Laboratory, Riken Nishina Center, Japan. And Professor Suparmi from Physics Department, Universitas Sebelas Maret, Indonesia. We also take this opportunity to welcome Dr. Ahmad Marzuki and Dr. Nuryani from Physics Department, Universitas Sebelas Maret, Indonesia as the moderators for today's conference. And last but not least, to our beloved guests and audiences, welcome to the International Conference on Science and Applied Science, ICSAS 2021. It is an honor for us to welcome all of you to this conference. We appreciate you taking time off your busy schedule to join us today. We hope this conference to be fruitful and engaging to all of you. Ladies and gentlemen, the next agenda, please join to listen our national anthem, Indonesia Raya. Please have a nice seat. Thank you. Let's continue to the next main agenda. To begin this conference, we are pleased to invite Professor Budi Purnama as Chairman of International Conference on Science and Applied Science 2021 to deliver the welcoming speech. Please welcome Professor Budi Purnama.
Assalamualaikum warahmatullahi wabarakatuh. Distinguished Vice Rector for Academic Affairs of Universitas Sebelas Maret, Profesor Ahmad Yunus. Distinguished Dean of Fakulti Matematika dan Ilmu Pengetahuan Alam, Dr. Harjana. Distinguished Keynote Speaker, ICSAS 2021, Profesor Andrino Frusdi, Profesor Satoru Yoshimura, Dr. Isa Watanabe, and Professor Suparmi. Thank you for your coming in here. Distinguished colleagues from Physics Department FMIPA Universitas Sebelas Maret and all the distinguished participants of ICSAS 2021. Ladies and gentlemen, in this precious moment, let us first express our gratitude to the merciful God who have granted us blessing and grace that we could gather here today to attend the 6th ICSAS 2021. Ladies and gentlemen, on behalf of the organizing committee, we are honored and delighted to welcome you to the International Conference on Science and Applied Science 2021. The International Conference on Science and Applied Science was the 6th conference which was organized by the Physics Department, Sebelas Maret University. On this occasion, the conference was held online on April 6, 2021, due to the COVID-19 pandemic. This conference is aimed to bring together the scholar, leading researcher, and expert from diverse background and application area in science. Special emphasis is placed on promoting interaction between the science and theoretical area and also experimental area and other topic related physics. In this conference today, there are 8 parallel sessions and 4 keynote speakers, invited keynote speakers. While for the conference participants, there is 303 participants were submitted abstract via the conference system. Then the 186 full paper which have been submitted from the participant, and after the review process, 156 paper will be presented to 8 parallel sessions in this conference 2 days. And then the 4 final decision paper will be published in Scopus Index proceeding. We deeply thank the author for their enthusiasm and high-grade contribution. The seminar would not be possible without the dedicated effort of many people who have worked with us in planning, organizing the program. We are grateful to volunteers who contributed to the various processes that make up the conference, and it would not possible for me to name them all in this submission. I hope that during this conference, you find conference fulfilling and enjoyable. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Budi Purnama, for the welcoming speech. It is now my deep pleasure to invite the Vice Rector of Academic Affairs, Universitas Sebelas Maret, Professor Ahmad Yunus, to deliver the keynote speech and to open the conference officially. Please welcome Professor Ahmad Yunus.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Distinguished the Dean, Faculty of Mathematics and Natural Science, Dr. Harjana, and distinguished Vice Dean for Academic Affairs, Vice Dean for Manpower, and Vice Dean for Collaboration and Planning. And distinguished also for Professor Budi Purnama, Chairman for this conference, and distinguished speaker, Professor Andrivo Rusdi from Department of Physics, National University of Singapore. Distinguished also for Professor Satoru Yoshimura, Research Center of Advanced Material for Breakthrough Technology, Graduate School of Engineering, Science, Akita University, Japan. Also distinguished for Dr. Isao Watanabe, Advanced Mason Science Laboratory, Riken Nishina Center, Wago, Saitama, Japan. And distinguished Professor Supardi from Department of Physics, Universitas Sebelas Maret, and all participants for this conference. At this precious moment, let us first express our gratitude to the merciful God who has granted us blessing and grace that we could gather here today to attend the 6th ICSAS 2021, with this year held in the Department of Physics, Sebelas Maret University. Let me extend my warmest greeting and welcome to our distinguished speakers and participants. This conference is one special event for researcher and lecturer to enhance the atmosphere academics, and it is an occasion for positive contribution, ideas, and knowledge sharing regarding the development of future science and applied science in Indonesia and other countries. Finally, we hope all participants of this conference can find important areas of common ground in the best way for achieving the broad goal. I have great pleasure in formally declaring this convention is open. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Ahmad Yunus, for opening the conference officially. Next on schedule, we will have a photo session. Please to our honorable keynote speaker and all of our participants to turn on your camera. Let's smile. Please to our honorable keynote speakers and all of our participants to turn on your camera. We will have a photo session. Please wait for a moment. Enough? Thank you. Excellencies, ladies and gentlemen, we will begin the first session of the plenary lecture that will be led by our moderator, Dr. Nuryani from Physics Department, Universitas Sebelas Maret, to carry this session. Please welcome Dr. Nuryani. Time is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. This morning is a special conference today. This is ICSAS. This time is the fourth plenary session. It is the first plenary session, and the next is the second plenary session. For the plenary session, the first plenary session is the keynote speaker is Professor Yoshimura from Research Center for Engineering Science, Graduate School of Engineering Science, Akita University, Japan. And the second keynote speaker is Professor Andrew Foresti from Department of Physics, National University of Singapore. Okay, for the first lecture, it is Professor Yoshimura. Good morning, Professor Yoshimura.
Good morning.
Okay, how are you today?
Yeah, fine, thank you.
Okay, thank you for your coming for this ICSS today, and this is very, very interesting for us to hear your presentation today. And you have about 20 minutes for your presentations. Okay, the time is yours, please.
Okay. Are you okay?
Yes, okay. I'm fine.
Okay. Thank you very much for inviting me to this wonderful conference. I'm very happy to meet you. Okay. And thank you very much for Buddhist chairman of this conference for your assistance. Okay, today I'll present about my research with this title. So, final goal of this my research is development of magnetic memory driven by electric field. So, to realize this system, I have to develop the multi-track material, and also I am measuring the dynamic magnetization reversal by applying electric field. Okay. Firstly, I'll introduce Akita. This is Japan here. And Tokyo is here. Osaka is around here. And Fukuoka is here. When I was assistant professor in Kyushu University, I stayed here with Dr. Budi-san. Okay, and after assistant professor, I moved from Fukuoka to Akita here, north part of Japan. And these are pictures around Akita. So we have clear 4 seasons. Now, very good season to watch the cherry blossom. And after that, we'll have summer. So Akita area, so north part of Japan, the temperature is not so high. So we have to enjoy summer. So this is a summer festival. And this is a rice field. Akita area is very famous place for rice field. And in this season, we can get new rice only one time. In Japan, only one time we can get the rice. This is a rice special food. So we often enjoy new rice. And this one, these are pictures for the winter season. So we have much snow like this. So temperature is very, very low. So situation is very serious, but we want to enjoy this season. So we have many winter festival like this. And also in winter season, hot spring is very comfortable. So in north part of Japan, there are many hot spring like this. Okay, these are introduction of the Akita. Okay, I'll move my top study. So as you know, so hard disk drive is very famous magnetic recording device, and the number of the production is very huge. However, this hard disk drive has many problems, such as writing system and structure, physics, and materials. These are details about the problem. So actually, in the case of hard disk drive, we have not so good future for example, low power consumption and high density recording. So new magnetic recording device with new writing method, low energy consumption and low cost are needed. 2004, so new physics for magnetism was demonstrated. So domain wall motion by spin transfer torque. So this one is electron with up spin. And these arrows are magnetic moment. And the domain magnetization is upward. Magnetization direction is downward. And this position is a domain wall. Firstly, we inject the up spin from here. Then up spin is rotated by magnetic moment. And the magnetic moment is rotated by up spin. So this phenomena is such kind of the action reaction between spin and magnetization. And at the time, the domain will move from this position to this position. And finally, so interface of domain and domain wall moves, and spin will be turned from up to down. This one is a new physics of the magnetism domain wall motion by spin transfer torque in 2004. And after 4 years later, IBM proposed the new magnetic recording device. The name is racetrack memory by using this new physics. So in this memory, there are many magnetic wires, and the magnetic wire has many recording bits. So the important thing of this memory is shock resistance and large capacity, because so three-dimensional recording will be realized by using this system. And domain wall motion will be done by spin injection with new physics. And this case, so motor free compared with the hard disk drive. So we can move the recording bit with low power consumption. Okay, so this is a so action of this memory. If we apply the current from this direction, the recording bit move from here to here like this. And after that, if we apply the current from this direction, recording bit move this direction. So in this system, so movement of the recording bit is has advantage about the low power consumption. Okay. However, this memory has also problems, especially writing method. Actually, to switch the magnetization direction of the magnetic nanowire, we have to use magnetic field from the coil. But this coil uses a very large power consumption, and structure is very complicated. So a new writing method is needed. I newly proposed the magnetic writing by electric field. Also, we need the new material for this method. Okay, so I'll introduce the new material. The important thing is the properties for magnetism and electricity. Bismuth FeO3 has ferroelectricity and ferromagnetism. And if we substitute the material like this, we can generate the ferromagnetism like this. Okay, so if the interaction between magnetic moment and polarity is strong, we can switch the magnetization direction by apply the voltage. In this system, there are many merits for reversal of the magnetization direction. This one is a concept of the high-performance racetrack memory with electric field lighting. This one is a normal racetrack memory proposed by IBM. Actually, in this memory, many coils are needed to write the information, reversal of the recording bit. So in my new system, we can replace from coil to multi-shell material here. Firstly, we apply voltage between this and this. Then we can generate the polarity here. At the same time, we can generate the magnetization here. And this magnetization can control the magnetic direction of the nanowire here. So I'll say this phenomenon is magnetization transfer. In this case, so this system doesn't need the coil here. So this system can reduce electric power consumption. For this system, we need the multi-shell films with perpendicular anisotropy and high magnetization is needed. This one is a film fabrication process. Actually, multi-shell material has very complicated structure. So film fabrication with high quality is very important. So if we use a normal film fabrication system, actually the film quality is not so good. So we have to change the fabrication system from the normal one. So this is our sputtering system. This system has a high frequency electric source at the substrate. So this electric source can generate the high frequency plasma around the substrate. So this plasma is very important for acceleration of the migration of the sputtering atom on the substrate surface. And I newly introduced the pulsed DC sputtering system. In this system, we can, this system will generate the minus voltage and plus voltage with like this. So in that case, in the case of minus voltage with high sputtering phenomenon will be occurred. And in the case of plus voltage, so in this case, electron can remove the surface charge. So we can reduce the arc around the sputtering target. And also, this system has many merits about the acceleration of the surface diffusion. So we can apply the very large power to sputtering target and with interval time. So this is very important for surface diffusion with a sputtering atom on the substrate surface. This is the result. The film fabricated by this system has high quality compared with the normal RF sputtering system. This is the previous result. In the case of the bismuth barium FeO3 film, this graph shows saturation magnetization of this material. The highest value magnetization is around 90 EMU per cc. This value is 1.5 times larger than compared with the normal RF sputtering system. This indicates film quality is very high compared with the normal RF sputtering system. These are typical hysteresis loop of this material. However, saturation magnetization is not so high, and magnetic anisotropy of this material is in plane, not perpendicular. This property is not suitable for the device application. Okay, these are the topics of my research. To show the possibility of the magnetic device driven by electric field, topic A, development of bismuth FeO3-based multi-electric film with perpendicular anisotropy. The second one is magnetization reversal and transfer by applying the local electric field. And topic 2 is measurement of the dynamic magnetization reversal by applied electric field. And topic 3 is development of bismuth FeO3-based multi-electric material with very high magnetization. This one is a film sputtering system. Okay, I'll skip this one. Okay, so topic 1A, development of material with perpendicular anisotropy. Basic material is bismuth FeO3, and there are many research about the substitution material here, A side and also B side. So from these research, this time I discussed about the bismuth A FeB03 material with A is lanthan, B is cobalt from these previous research. Okay, so I'll show the property of this material. Red one is magnetization, and blue one is so okay. Out of plane coercivity is larger than the in plane, like this. This one is a hysteresis loop of this material. Coercivity and remanence of the magnetization is larger in the case of out of plane compared with the in plane. So, perpendicular anisotropy with relatively high saturation magnetization was obtained in this material. So, this perpendicular anisotropy is very important for device application. This one is a topic 1B, magnetization reversal and transfer by electric field. This one is a surface of this multi-electric material. Before apply the electric field. After apply the electric field by using the AFM with 10 volt with this area. After that, we can, so I can generate the magnetic domain like this. And also, we can observe the polarity at the surface of this material. And also, we decrease the width of the area of the applying the voltage from 500 nanometer to 100 nanometer. This discussion is very important for device application because recording device, in the case of recording device, bit size is very small. So we have to control the magnetization direction by apply the electric field with very small area is very important. From this data, around 300 nanometer size, we can control the magnetization direction. So magnetization reversal was realized by electric field. However, important measurement is magnetization transfer by applying the electric field in laminated film. Because this one is a device image, magnetic nanowire here, and multiferric materials here. So I fabricate this structure similar to this device. Multiferric material here and metallic magnetic materials here. And before apply the voltage, this is the MF image. You can see the black part, white part randomly. This indicates the demagnetized structure. After apply the voltage, only this dot here. After that, the MFM image is this one. This dot has black part, white part randomly, no change. But this dot applied the voltage. So you can see the white compared with this one. This is a line profile of two dots. In the case of this dot, we can see N direction and S direction is equal. But after apply the voltage, downward magnetic moment of 75% was reversed to upward by applying an electric field. So this indicates a demonstration of magnetization transfer from here to here was a success. However, important measurement of the dynamic magnetization reversal by applying electric field is important. So because real-time magnetoelectric effect is also important. So this one is the topic 2. This one is a normal system for measurement of the MH curve. And also this one is a normal system for the measurement of PE curve. But important property is this one, magnetoelectric effect, magnetization against the electric field. But we have no system about the measurement of this one. So I newly developed the magnetoelectric effect measurement system. I combined the magneto-optical Kerr effect system and ferroelectric testing system like this. By using this system, we can measure the magnetization direction with applying the electric field. So dynamic change of the magnetization direction against electric field will be measured. These are the pictures of the new system. And this is the result. The film structure is similar to the previous one. Multiferric materials here and metallic magnetic materials here. And this one is the image curve of this material. And this one is a Kerr loop of this metallic magnetic material. And this data is magnetic Kerr effect of this material against the electric field here. So you can see the hysteresis here. So this indicates magnetization direction of this material will be was measured with during the application to the electric field. But magnetization transfer was not sufficient to realize the complete magnetization transfer. Development of film with very high saturation magnetization is necessary. So, okay, I'll move to topic 3, development of new bismuth FeO3 based multi-check material with very high magnetization. I discussed with many material for the substitution. A side here and B side is here. In the case of the neodymium, very high saturation magnetization was obtained. And also, this material has large coercivity with perpendicular plane. And also, the anisotropy, magnetic anisotropy is very high. So, okay, this material has a very large saturation magnetization with perpendicular anisotropy. So this material is suitable for the application to the magnetic device driven by electric field. Okay, this is a summary. So for realization of novel and high performance magnetic device, identify of issue of current device, and proposal of new system which solve the issue, and fabrication method for high quality film material, and development of material with improve the system performance, and finally demonstration with the device action by new measurement system are needed. Okay, thank you very much for your attention.
Okay, thank you very much, Professor Satoru Yoshimura.
Thank you.
It is a wonderful presentation. There will be discussion, but before the discussion, the other speaker will deliver the presentation first, and after that, the discussion will be started. Okay, again, thank you very much.
Okay, thank you.
Okay. Ladies and gentlemen, the next plenary lecture is the presentation by Professor Andri Forsti. He is from Department of Physics, National University of Singapore in US. Okay, good morning, Professor Andrifo. Okay, I think it's...
Good morning, good morning.
Okay. Good morning. How are you today?
Alhamdulillah, good. How are you today?
That's good, thank you. Okay, thank you very much that you are available to present your research for ICSAS today. I think it's of course, it's very interesting presentation. Okay, you have about 20 minutes for your presentation. Okay, and the time is just please.
Okay, one moment, I'm still trying to get.
Okay, it's fine.
Slides,
yeah, it's fine. Yeah. How is situation in Singapore? It's good.
Very good.
Yeah.
We are doing all right. And
Yeah.
okay, let me start to get the time.
Okay.
So,
Yes.
Pertama, Assalamualaikum warahmatullahi wabarakatuh. Pertama, terima kasih pada Profesor Budi, adik-adik yang sudah menyelenggarakan webinar ini. And today, I will spend 15-20 minutes to discuss my own research interest and how to generate new science and new technologies. And I use references here. And today I'm going to talk more like a new discovery by us about spin plasmon, so spin-coated plasmon, using new material based on gold, which we name it highly oriented single crystalline gold quantum dots. It's a new type of material. It's based on gold. So you can look at the references, our scientific papers. You can look at our Google Scholar, just to get adik-adik semua, you can refer to what we discussed today. And since the time is very limited, I'm going to show you a little bit whatever we discussed today has been published in Google Scholar. So you can pick up anything that you like from our references here. And some of our publication published in Nature, Science, Physical Review Letters. And if you don't have the access to those, you let me know so we can send you the references, because it's very important to read whatever we're going to discuss today. Yeah. So my own interest is actually based on the Al-Quran, where I personally want to understand Nur. What is Nur basically? So Nur, which is today we learn about photons, yeah, about photons. And I've been studying Nur since maybe like when I was 6 years old by my teacher, Buya Hamka and Palimo Kayo. And my teacher has a teacher of Sheikh Abdul Karim Amrullah. And my teacher is Sheikh Ahmad Khatib Al-Minangkabawi. So I learned Nur for 35 years just to think about photons. And the photons after 35 years, alhamdulillah, we make our own facility to play with Nur, to play with photons. This is based on the synchrotron light source. So this is Singapore synchrotron light source. What you see here is my own lab. So my lab, in this lab we can growth material, we can growth basically, I can play with photons from very broad energy range from half an eV, 0.5 electron volt, all the way to 1,500 electron volt. So this is unique and the only facility that we can do this. So what we can do is, the next thing is actually, I want to couple this Nur with another ayat called with Zarrah, but this time the Zarrah is actually spin, charge, orbital, and lattice. So my research is actually how to couple photons with spin, charge, orbital, and lattice, and see what we can get out of it. So 35 years of research, 40 years of research it takes a while to understand the ayat. Okay. So what we want to generate is actually, I want to create kue lapis. Okay, this is what I want to make. I want to make kue lapis, but each of the lattice here is individual specific atoms. For instance, first layer is copper, second layer is oxygen, the next layer, for instance, lanthanum. So I can make them alternating based on what we wish. Okay, and to get to this point, you need actually photons. You can use photons like your fingers and put this atom by atoms. So this facility we already published in the Review Scientific Instruments. So you can take a look and you can see this gentleman, and to align everything here. So we growth the material, we growth our kue lapis over here and transfer from one place to another place in situ. In situ means there's no air. So you can really want to control each of the atoms without contamination, air contaminations. Because the reason is that we want to understand the intrinsic properties and bring out technologies out of it. Okay? So what we can do is actually with this facility, I want to create so-called intelligent materials, material that not exist in nature, but it's actually allowed to make it because the Al-Quran allow me to do this. So I can control the exotic properties. I can make material become not naturally happens, but change the properties dramatically from, for instance, metal become insulator, non-magnetic become ferromagnetic, opaque become transparent. Okay, all these things supposed to be able to do that if we understand the quantum physics or the wave function of the material. So, so the flow of my research, the future technologies that I want to generate, that I wish to generate, is actually something like miniaturizations, something extremely small in nanometer scale. I would like to have something fast and fully controlled by the photons, so by light. So that's actually the fast speed that you can get, and energy, low energy consumptions. That is where we have to make use of Nur coupled with Zarah. So it's light matter interaction. And our Zarah today, what we discussed earlier, is spin, charge, orbital, and lattice. So the way that I make my research from my earlier times is that I take the Al-Quran, I take the ayats, and then take that from become like new science, and then write papers, write a lot of good papers. And then from there, you collaborate within academia and industry. So we also have industrial collaborations. Yeah, to collaborators, we collaborate with industry, so then we can make use of what we make in the lab, become new technologies. And this today, what I'm going to give you in the next 5 minutes slide, because time is running very fast, is that another ayat that I'm actually doing research for the past 10 years is that can we modify fundamental properties of gold and silver, which is opaque, okay, become transparent? And that's ayat actually telling me it should be able to be done if we know the recipe, but it took years and years to get the right recipe. Yeah? So I'm going to use, again, the technologies based on the photons, the ayat that I learned for 35 years, and to generate and make use of the facility that we build up from scratch. So yeah, this is really from scratch. You have to calculate everything and put everything fundamentally correctly. And then from this, what I want to make is that, can I modify this goal that you see here, become something uninterested for the human, but it's extremely important for fundamental science and future technologies. Okay, so now I want to show you that the question that I want to make is that gold naturally is the noblest elements. Color is yellowish. It's opaque, not transparent, metal, and non-magnetic. So my wish now is actually to modify all these properties and see I can use for future new technologies, for instance. And this is the research done by my group, yeah, with my postdoc and students, that doing along this research to understand this phenomena of gold, we discover new phenomena, so-called spin plasmon. So plasmon is not just quantized of electron anymore, but spin, a quantization of spin, C of spin. And we also create new material called with highly oriented single crystal gold quantum dot. So this is not the same with quantum dot of gold or nanocrystal or nanoparticle of quantum dot. This is really unique gold, and is accepted now in the paper Nature Communication and Nanoletters in the sense, in Nanoletters. And this is what you see here, that by doing research using the facility, we have gold, which is yellowish color. We make it now transparent with a different color. So we can make green transparent, red gold transparent, purples, golds. And you see here, they are very much like what we wish, and they can fulfill. This happens because we are able to make the gold. Yes, gold is actually oriented with a specific condition. And what is really important is that along this line, if you look at this, we are actually working also closely with industry. So this is TechnoSpec with industry in Singapore to make use of this gold, to make use of the spin corrected plasmon, the new phenomena, to detect a system, biological system. So just go back here a bit. If you look at here, so it depends very much how we grow the material, the color of the gold, which was just yellow color. No, it's no longer just a yellow color, but different type of color, and they're all transparent. But it's not only transparent. If you look at, for instance, the spectroscopic ellipsometry, where you can see the complex dielectric functions, you can get the Drude response completely suppressed. So you create a gap, and you can vary the gap from 1.5 eV to 2 eV. And that's actually very important, because this gap is also important for the various type of application, including water splitting, for instance. So we have discovered new material now, and this new material that we currently use to detect quantum to use for biological system. So we can make use of looking at pathogens, viruses, and bacteria. Yeah, so we are collaborating not just academia, but also with industry to make use of this new technology, which are based from the Al-Quran that I took earlier. Okay, so conclusions is that my conclusion is very simple. Okay, let's do research, very serious research, and let's collaborate. Yeah, we should really collaborate. We should really collaborate among each other. And practically for me, it's actually part of my Islam religion that we have to make use of. We need to get the ilmu yang bermanfaat, and this is part of the sadaqah jariyah. Assalamualaikum warahmatullahi wabarakatuh.
Okay, Waalaikumsalam warahmatullahi wabarakatuh. Okay, it is a wonderful presentation. I think that the nur is photon. Yeah.
Nur is photon.
What I know, the nur is light. Okay, and the zara is spin, orbital, and so on. What I know, the no zara is atom in the past, or the bigger the end. Atom. Yeah. Okay. Okay. Thank you again for your presentation. Okay, ladies and gentlemen, we have another 30 minutes for discussion, and you can ask to our two distinguished presenters or speaker today. Okay, I open the discussion. Okay, please, your question. Okay, any question? Okay, maybe still need time to make a question. I want to ask to Professor Yoshimura. Okay, Professor Yoshimura is still there? Okay, I want to ask about the advantage of the multiferroic compared to the just ferromagnetic materials. What is the comparison? Okay,
okay. So actually, important thing of the multiferroic material has two properties about ferromagnetism and ferroelectricity. And generally, the relationship between magnetic moment and polarization. So some material is strong, some material is weak. But if we can use the material with very strong interaction, we can control the, for example, polarity by applying the magnetic field. And we can control the magnetization by electric field. So, okay, today I indicate the application to the magnetic memory, but this material has many possibilities for device application. I also study about the display device. Future display device by using this multiferroic material, and details so will be skipped, but that new display device is very important for that kind of the multifunctional properties. So I think that this kind of the multiferroic material has many future for device application. However, for example, in the case of the magnetic property, so this multiferroic material is now not so high. Also, the electric property is not so good compared with the simple ferroelectric material. So important thing is improvement of the each properties in multiferroic material.
Yeah. Okay. Thank you.
Thank you.
Okay. Any other question from the participant? Okay, if there is no question, I want to ask to Professor Rusti. That I said before that the Nur is photon and the Zarah is the spin orbital, and in the past is an atom or the bigger ends. Okay, is there any possibility that the Zarah is more small and smaller again in the next?
If you look at from the size, electron is 10 to the minus 18th meter. So you need to prove it if there is something smaller than electrons. So understanding of Al-Quran is not just thought. You have to prove and show that you can generate science and technology out of it. And it's useful. So there's always possibility. And in the past, when I was a kid, Zara is actually increased something even bigger.
Yeah. Yeah.
So it's no longer atom, it's spin, charge, orbital, lattice. It's quantum physics to understand Zara.
Yes. Yeah, I know. Okay. Okay. The next question is, in general, what is the very significant contribution of the theory of physics for the science in the Islam, especially for Al-Quran, for understanding the Al-Quran?
Okay. So first of all, you have to look at the fact is experiment.
Yeah.
Okay. So get the fact, and theory is trying to understand a model from experiment, not the other way around. Okay. So you get the experimental data, apply a model, and that's a theoretical physics. And then if the model is correct, then you can generate a simplified model for specific case. And from the model that you have, you can generate technology out of it. So theoretical physics alone, without the fact, might not be directly relevant to our everyday life. It's still important, but might not be directly relevant. What we want to generate is that how we being useful for others, and technology is important. So you need to create technology and collaborate with everyone from experiment and theory. So experiment alone without the theory also not easy to get it become technology, because you still need equations.
Okay, thank you very much. Any question to participant? Okay. Okay. This is the question for participant. Okay, this Professor Budi Purnama. Okay, please, Professor Budi Purnama. Yeah, Professor Budi Purnama.
Okay, I just one question from Professor Satoru Yoshimura. Okay, itu Prof. And your sample, you use the PMA material for the memory, for the magnetic memory.
Yeah.
What the scenario to the reading in the system?
Sorry.
What kind of scenario do you use the read and write mechanism in your memory scenario?
Mechanism of the memory?
Yes.
Okay.
Usually PMA is high saturation magnetization, and this is the required very high magnetic field.
Yeah. So important thing with this device is magnetization transfer from multi-electric material to metallic magnetic material. So actually, the important thing is the control of the magnetization direction of the metallic nanowires. And actually, magnetic field from magnetoelectric material is very important to control the magnetization direction of the metallic material. And, now, the magnetoelectric saturation magnetization of the magnetoelectric material is not so high. So if we can increase the film thickness of the magnetoelectric material and we reduce the film thickness of the metallic magnetic material, then we can control the magnetization direction of the metallic magnetic material. But for the device, actual device application, both very thin magnetic layer is very important. So size and also the value of the applying voltage. So reduction of the film thickness is very important. In that case, with decreasing the film thickness, we have to increase the saturation magnetization. This is a very important thing for device application in the case of the magnetoelectric material. And previously, the saturation magnetization was not so high, but these days, I discussed about many material, substitution material. Then the saturation magnetization increase. Future, I'll discuss about the many other material. So I hope I can increase the saturation magnetization. Then I can realize the complete magnetization switching by transfer. Thank you very much.
Okay, thank you, Professor. It is the question in the chat. This from Universitas Indonesia. Okay, I read the question. I do have this for Professor Yoshimura. Okay, I have a question. It is something about anisotropic condition required in the multiferric system as a CD reader. I think that is the idea. Is it possible to find this condition with the anisotropic system, such as the use of the biological material, such as wood? Okay. Thank you.
Okay, so my major is physics. Not so familiar about the biological and also other, for example, chemical part. So, so now I can say we will have the application to these fields, but now, so I often discuss with many other researchers with different fields. So some researchers interested in my research. So future, I think I'll have a chance to collaborate with that field. So, but now I can say this one. Thank you very much.
Okay, thank you. Yeah. Okay, the other question in the chat room is for Professor Andri Foresti. It was explained about the gold nanodot for the biology, virus, and the bacteria. Can you explain more about this? Yes, please.
Okay, all right. So that's very good questions. So if you know, for instance, SIRS, spin enhanced Raman spectroscopy, and what we actually found in this new type of quantum dots of gold is spin SIRS is related to helical structure. And if you look at the origins of cell, is actually related to spin. So we can look at left and right spin helical structure. So it's very important to look at the living cell in the future, and we can distinguish them. We can see the contrast between different pathogen and viruses because we can tune the energy or the resonant conditions. And that's actually also quite cheap, because you can one of the problem right now with the nanoparticle is reproducibility is very low. So you make one time, you make the second time, it's not exactly the same, never been the same. So that's one of the problems to make them standardized. Now with the new type of gold that we produce, we hope that we can have the standard so-called the sensitivity with a number of merits. So we have to identify quantitatively and qualitatively. So it's basically, this has become like open chapter. So I'm very optimistic in the sense, if you apply this into your material, you should see a contrast, very strong contrast, and you can do this in room temperature. You don't need to cooling down the system, because otherwise industry will be very expensive. Yeah, so I hope that answered a little bit. There's a lot of things, so you can read my papers related to this about spin plasmon, spin coated plasmon. That's actually, we found it earlier in other system.
Okay. Yeah, thank you very much. This. Okay, ladies and gentlemen, any other question? I think this is the very nice speaker today. Any other question?
Ya, oke, Pak Nur.
Ya, please.
Untuk Pak ini, untuk Prof. Rusdi, Andrina Rusdi. How to confirm layer by layer in the multi-layer system in your sample?
Right, very good. So we have, okay, let me share you the screen again. One moment. Yeah. So you have to look at first in situ characterizations. In situ characterization means you have, when you grow the system, you are able, I have the photons now, we can detect the structure and at the same time electronic structure. So you need both crystal structure and electronic structure. Electronic structure, we identify a specific orbital of electrons, so you can see whether your gold is actually expected as an insulator. If it's insulator, what's the energy of the gap, for instance? So you need to identify that in situ. And we make the system that we can identify that in situ. So you know that precisely you can do X-ray diffractions, and that X-ray diffraction, you can spot it precisely. And not only that one, you can identify how they grow layer by layer. So you have to see a read pattern. Okay, so one layer, the second layer, the third layer, etc., etc. And then you can identify that how, whether they are hexagonal or cubical, we can identify that quite precisely because we have the system stabilized for that condition. So, but the final mark here is that you have to be able to measure magnetism. That's why we use the synchrotron technique, what I haven't discussed it today, so-called X-ray magnetic circular dichroisms. There is a technique that I developed earlier with my supervisor, so-called resonance soft X-ray scattering during my PhD time. So we use that to see the charge distributions in the system. So you need to understand how the inhomogeneity of your electrons in the entire system, because you want to make your gold transparent. And that's a real challenge, how to move the oxygen, the electrons in the gold, in the specific orbital away from the truth response. So you need to have a complex characterization in situ to make gold transparent and reproducible. Hopefully that's helped.
Okay.
In situ system, yeah.
You need in situ. Otherwise, once you bring gold out, you have various type of gases will be sitting on top of it, and that's everything. If you change the surface, you actually change. You also change so-called interface, because surface and interface are connected among each other for nanometer scale.
Okay, very interesting. Thank you very much.
Okay, thank you very much. Any other question from the participant?
Okay, Pak Nur.
Okay, yes, please, Prof. Chari from UNS.
This is for Prof. Rusdi. I get some maybe still confused about the Shara. That's mean your interpretation, the smallest particle or small particle like a photon or electron or something that. This your interpretation about the particle from Shara.
Yeah.
But I mean, is it the smallest? Shara means smallest particle or just small particle?
No, it's actually more than, it's not about the smallest particle. It's something that you can make use of it. Something tiny, the smallest thing that you can make use of it. You can utilizing it. So if you can utilize electron, that is your Zarah.
Oh, okay.
Okay. If you utilize biji sawi, that is your Zarah.
Okay.
Okay. So I'm utilizing electron, which is 10 to the minus 18. So I have to be responsible for my electrons now. That is my Zarah.
My Zarah. Oh, okay. This is your interpretation, right?
It's not interpretation. It's the fact. It's the data. Is the smallest that I can play right now is spin chart orbital lattice. So it's no longer interpretation, it's fact. Otherwise, you cannot use to make technologies.
About another particle?
It can be, but you have to make use of it first.
Okay.
You have to be able to control it.
Okay.
So that's what the question of Dr. Nuryani, the same thing. Theoretical physics is important, but then you need to look at what is the fact. So right now, smaller than electron, there's called quantum number spin, which is actually very important. And then you can make use of spin for quantum computing. That is another Zarah. And that is actually quantum properties of the electron, even smaller than the electron.
Like pion particle, like something that is
yes,
smaller.
That can be another, exactly. But the pion particle is actually bigger than it's a size of the electron. So electron remains smallest.
Oh, okay. Okay. Thanks.
Okay. Right. Okay.
Okay. Yes. Any other question, please? Any other question? Okay, if there is no question, thank you very much for Professor Satoru Yoshimura and Professor Andri Forusti. I think this Hamka student, yeah. Okay, yeah. On behalf of the ICSAS committee, we say thank you very much for your wonderful presentation, and we invite you to Indonesia, to Solo, after the Corona pandemic finish, I think. Yeah, maybe in the next time or in the next year or sometimes after the pandemic finish, please come to Solo. I think this the wonderful city and small city in Indonesia. Again, thank you very much for the nice presentation, and I give the time to the MC. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh. Thank you, Dr. Nuryani, for being the moderator for the first session of the plenary lecture. We will continue to the second session of the plenary lecture with our moderator, Dr. Ahmad Marzuki, to carry the session from Physics Department, Universitas Sebelas Maret. Please welcome Dr. Ahmad Marzuki. Time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Yeah, good morning for everybody. Thank you very much for joining to the conference, International Conference on Science and Applied Science 2021. I hope you all are very well now, wherever you are. Okay, today this morning, I will moderate two talks. Yeah, the first talk is will be delivered by Professor Suparmi, and the second talk will be delivered by Dr. Isao Watanabe. Okay, before we commence with these talks, and I will maybe deliver the role for you. So for each presenter, we will allocate time for about 20 minutes. So 20 minutes for Professor Sparni and 20 minutes for Dr. Watanabe. Okay, I hope everybody's ready now. Okay, the first talk will be delivered by Prof. Sparni. Prof. Sparni, are you ready, Prof? Okay, thanks. Okay, time is now yours, Prof. Okay, you can start your to deliver your presentations. Okay, Prof.
Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay. Good morning, everybody.
Okay, good morning, Prof.
Okay, maybe my talk on the PowerPoint will be sent from the campus. Please to stop for the PowerPoint. Today I want to talk about the solution of Klein-Gordon equation that is coupled directly by quadratic vector and scalar potential using Nikiforov-Uvarov function analysis and its application for optical properties. And this study I just start the new one. And maybe today this is the first time I will discuss about new thing. So maybe people can help me to understand this new thing. Okay, next. Okay, really the optical properties of the low dimensional semiconductor can be determined using the energy spectra and wave function that obtained from the solution of Schrödinger equation. Here I talk the solution of Klein-Gordon equation, and then by using the approximation that's the relativistic energy and non-relativistic wave function can be directly changed into the non-relativistic energy and wave function. And then after we obtain the solution of the Klein-Gordon equation, then we will change the energy relativistic and wave function into non-relativistic one. And then after we get the non-relativistic energy and wave function, this data can be used to determine the optical properties of the low dimensional semiconductor. Next, please. The low dimensional semiconductor is usually called as quantum dots. One quantum dot consists of one electron and hole, and this pair carrier charge can move into three-dimensional system. and they also can be confined by any potential energy, and then this quantum dots can be considered as an atom, but is bigger than the atom. The measure of the quantum dot, one quantum dot is around few tens nanometers. And this quantum dot is extremely very vaccinated because of its characteristic. If an atom, we have energy of electron that is orbit into the nucleus. So the quantization of the electron energy depend on the orbital of its electron. But in quantum dot, the quantization of energy of one pair electron and hole is quantized by subband. The behavior about quantum dot is look like similar with the atom. There is transition energy. Electron can moving from one orbit to another orbit. Here, one pair of electron and hole also can can have transition from one subband to another subband. And the difference between the energy of quantum dot between subband is much bigger than the difference of energy of electron between two orbital. And therefore, a lot of energy potential have been used to investigate about the theoretical energy of a pair of electron and hole that depend on the energy potential. And some of the energy potential usually called as shape invariant potential, and some already be used to investigate the theoretical energy in the subband, and also the transition between the energy of a pair of electron and hole intersubband. Next. And therefore, here we try to find some new energy potential, and sometimes the energy potential can be found, can be regarded as new one by using some screen parameter. So today I want to talk about the relativistic energy and non-relativistic energy of a pair of electron and hole that is influenced by vector potential and scalar potential that is coupled directly to the Klein-Gordon equation. Next, please. Okay. In order we can get the non-relativistic energy, relativistic energy, and wave function, we have to solve the Klein-Gordon equation that is coupled directly by quadratic vector and scalar. Hello. So here
Okay, Prof. Just go on, Prof.
Okay. To obtain the non-relativistic energy and relativistic energy and also wave function. We will solve the Klein-Gordon equation that is coupled directly by the quadratic vector potential and non-central scalar potential by using Nikiforov-Uvarov function analysis. Usually people using some method in solving the Schrödinger-like equation, such as Nikiforov method, hypergeometric differential equation, IM, and then supersymmetric quantum mechanics, and then factorial method, and some special method like Legendre differential equation or Laguerre differential equation. Today I will use Nikiforov-Uvarov function analysis to be used to solve the Klein-Gordon equation. Actually, Nikiforov-Uvarov function analysis is a method that is a combination between Nikiforov-Uvarov method with the hypergeometric differential equation. So here we will using some formula that had been derived from Nikiforov-Uvarov method and also from hypergeometric differential equation. And after we use the Nikiforov-Uvarov functional analysis together with using the variable separation method. Next, please. Okay, today this equation for Nikiforov-Uvarov functional analysis start with the statement of the differential equation. This is like a specific differential equation that is developed by hypergeometry differential equation, but this is more general than the usual hypergeometric equation. This equation that expressed in equation 1 is actually can be obtained from the one-dimensional Schrödinger equation for shape invariant potential by using a new variable, and the new variable usually already derived from some shape invariant potential. Next, please. This is we have one-dimensional Schrödinger-like equation for shape invariant potential, and then by using some new variable substitution, we will get the differential equation that is combination between NO and hypergeometry differential equation. And then to solve this combination of differential equation from NO method and hypergeometry differential equation, we have to introduce a new wave function. C is equal as power of lambda multiplied by 1 minus alpha 3 as power of gamma multiplied by any function f. And then after using the new wave function, the differential equation that is a combination of NO and hypergeometry will reduce to the another formula. Next, please. Kok ano ya, ada yang hilang ya?
Mohon Mas, ada yang anu Mas. Ya.
Lah yang sebelum kondisi dan sebagainya itu nggak ada.
Sebentar, Prof. Teman-teman bisa.
Sebelumnya sebelum. Lah, ini ada yang hilang setelah Gauss hypergeometric equation ini.
The committee can hear that.
Okay. Yeah, actually we just plugging the new wave function C that is equal to S power of lambda time blah 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 into the left equation, and after we do some mathematical calculation, and then we will get I think a long mathematical expression. Then by using the condition, then the mathematical expression will reduce to Gauss hypergeometric equation by some condition. So this is the sum that gone. Okay, next. Okay, from the condition, in order, this is right one. Okay, so after plugging the new wave function into the left equation, we will get the Gauss hypergeometric equation. This is standard hypergeometric equation. By using the condition, there is two equations that have to be set to be 0. This condition, yeah, this is actually before together with the Gauss hypergeometric equation in some expression. After setting this equation to be 0, then okay, we will have the value of lambda and gamma. Lambda and gamma is the power of the new wave function that introduced. And then from this condition, from the Gauss hypergeometric equation, we get the equation for the energy that is called, yeah, n square plus 2n square root of alpha 3. This is equation for the energy. By finding the value of n from this equation, yeah, this is on the energy equation. So after we put some parameter like lambda and gamma that already shown above, and for certain potential that we use, so we will get alpha 3, lambda, gamma, alpha 2, alpha n ke si 1. This parameter is obtained from the Klein-Gordon equation for the certain potential that by using variable substitution and wave function from Klein-Gordon finally reduced to the Gauss hypergeometric function. Okay, and in order to determine the wave function, we have to find the A accent, B accent. This is related to the hypergeometric polynomial. Okay, next. Okay. A accent, B accent, C accent will be plugged in the wave function of the system. Here, the wave function for Klein-Gordon equation. Yeah. So I said before, then the alpha 1, alpha 2, alpha 3, ke si 1, ke si 2, ke si 3, all are the parameter in the second order differential equation that is combination between NO and hypergeometric differential equation. And this is the system that we will investigate about the solution of Klein-Gordon equation that is coupled with quadratic vector potential and quadratic scalar potential that is shown in the below one. Okay, next. This is okay, and then we write the Klein-Gordon equation in using spherical coordinate by couple quadratic vector potential and scalar potential, and then in order we can solve this Klein-Gordon equation, we have to use the variable separation method to separate the radial, polar, and azimuthal wave function. Next. And then after using the variable separation method, then we have the radial Klein-Gordon equation that have the form similar to radial Schrodinger-like equation. We also get the polar Schrodinger-like equation and azimuthal equation. So we have three differential equation, second order differential equation, and the first one and the third one will be solved using NOVA. But for the middle one, for polar Schrodinger-like equation, is solved using associated Legendre polynomial, because this form of differential equation is similar with associated Legendre polynomial. Next, please. First, we have to solve the radial equation of the Klein-Gordon equation. From the solution, we will get the energy, relativistic energy equation, and also we will get the radial wave function. As I said before, this Klein-Gordon equation for radial path will solve using NOVA. So the last equation is we call as a Schrodinger-like equation in one dimension with a variable R. Please, next. And by using new variable, we set cosine hyperbolic alpha R equal 1 minus 2z. And then by using new variable, the radial Klein-Gordon equation will reduce into the second order differential equation with variable z. And then this differential equation with variable z, we rearrange. So we get the general differential equation for NOVA as I wrote in the first equation. From this general differential equation of NOVA, then we compare between this differential that we derive with the first one. Next, please. By comparing the equation from the first equation, differential equation that is combination of NO and hypergeometric with the second order differential equation with new variable for radial part of Klein-Gordon equation, we get the parameters expressed in equation 30.
You have 5 minutes left, Prof.
Okay. So here we have equation 30, and then from the condition we get the value of lambda and gamma, and then from these two equations we can determine the non-relativistic energy that we got from the equation relativistic, and then we get also the radial wave function. Next, please. This is the equation of the relativistic energy. Next, please. And this is the equation of the non-relativistic energy that is obtained as approximation for relativistic energy. Next, please. This is the numerical value of the non-relativistic energy of electron binding that is influenced by quadratic vector and scalar non-central potential. But here in the calculation, we set the parameter capital G and capital C is to be set to be 0. Next, please. Here is we have two tables for energy for L equal 0 and L equal 1 for some radial quantum number n, and for some different value of V null as a depth of the potential. Next, please. As I said before, after we get the parameters and we get the value of lambda and gamma, and also automatically we will get the value of A prime, B prime, and C prime, and so we will determine the wave function. Okay.
Go on, bro.
Okay. Okay, next, please. This is the wave function for radial part that have to be determined by using the parameter that we already got it, and also the value of lambda and gamma. And if we will determine all wave function, radial wave function, polar wave function, and azimuthal wave function, so we can just multiply of each wave function. Okay, next. All that we did to determine the energy, non-relativistic energy, and non-relativistic wave function, particularly for radial 1, and all the determination will be used to determine the optical absorption coefficient and refractive index of quantum dot. Here, quantum dot is mean that is a low-dimensional semiconductor. And to determine the optical absorption, we have to interact the material with the electromagnetic field. So in this equation is showing the electromagnetic field equation with omega as a frequency, and this is radiated to the material of quantum dot. And to determine the optical absorption coefficient, people already use the metric elements that is calculated from electron density operator. Rho is electron density operator. And then by using this formula, next. Okay, this is the first equation, and second equation is the susceptibility of the material quantum dot. And here already we explained that MIG is the expectation value for the field that is applied to the quantum dot. Next. and after determine the susceptibility, and then we can determine the absorption coefficient of the optic. So this alpha 1, alpha 3 is this is the absorption coefficient. Okay, next please. Okay, so here in this investigation, I just determine the energy relativistic and non-relativistic, and so on the wave function, but the optical absorption and the change of the refractive index will be determined next. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Prof. Suparmi, for a wonderful talks. And we will have discussions after Professor Watanabe delivering his talks. Okay, thank you very much, Prof. Parmi, and we wait for another 10 minutes, and after that we will have a discussion. Okay, ladies and gentlemen, this is the presentation from Professor Suparmi. If you have any question, please write down your question on your paper, and we will have discussions after Professor Watanabe delivering his talks. Thank you again. Thank you very much for Professor Suparmi for this wonderful talks. Okay, now we move to the second talks. The second talk will be delivered by Professor Isao Watanabe. Professor Isao Watanabe is a researcher from Mason Science Laboratory, RIKEN. Is it right, Professor? How to read that, RIKEN or RIKEN?
Hello, can you hear me?
RIKEN, yeah. RIKEN is Ishima Center, Japan. To know further about Professor Isao Watanabe, Professor Isabe maybe can introduce by himself. Professor Isao Watanabe will have 10 minutes allocated for you to deliver your talks, and we will have question answer soon after that. Are you ready, Professor Isao Watanabe?
Yes, I'm ready to go.
Okay, time is now yours, Professor.
But could you please wait? Could you please stop the screen sharing from your side? I cannot share the screen.
Okay. Okay. Hello, committee. Professor Isao cannot share screen, so please allow him to, in order to able to share his screens. Hello.
Hello.
Mas,
sorry, I cannot start my video.
Tolong di share screen-nya, Mas.
Can you see my screen?
Okay. Yeah, okay. I can see your screen now, Professor.
Good.
Okay, great.
Great. I start my talk. So thank you for the.
Is it correct?
It's okay.
Yeah.
Wait. Something wrong. Okay, can you see my screen?
Yes.
Can you hear me? Okay. Okay, so thank you for giving me a good opportunity to talk about my the research on the superconducting state in your very valuable conference. I'm very happy to talk about what is superconductivity in front of you, but my talk time is very limited, just like 20 minutes or so. So then I'd like to talk about just introduction. What is a superconductivity? So my name is Isao Watanabe from RIKEN, working in Japan, near Tokyo. So superconductor, as you know, there are many applications by using superconductors. So then there is still the strange materials to be studied in front of the top physics. So this is just only like an image. So then in the beginning of this century, what was the top physics on the, how can I say, solid physics is how is the resistivity at low temperature side. So this is a typical image, typical behavior of the metals, metallic property. If you measure the resistivity by using a metal just like a copper, zinc, or iron, the resistivity shows like a linear temperature dependence with decreasing temperature. But in the beginning of the 20th century, nobody knew about the resistivity at low temperature side. That is going to be 0 or that going to be like a residual values. So this was the top physics. So how do they answer to this question is they need a cryogen to cool down the samples. So then at that time, there was no liquid helium to get low temperature just like below 10K or so. But recently, we know how to cool down the samples down to like a couple millikelvins. So then we can know about the typical behavior of the resistivity even at low temperatures. But 100 years ago, this was just like a top physics. So then the liquid helium is definitely needed to cool down the sample temperature to carry out this study. So then what is the resistivity? Okay, the resistivity, how to understand resistivity is very important to understand the superconducting state. So what is the origin of resistivity is the vibration of the lattice. This is just like an image, schematic image of the resistivity. So atom, iron, that means the atomic atoms in the material. So atoms, they has arms, so then they connect each other and making a lattice, okay? So lattice means just like crystals. So when the electrons are passing through this lattice, the lattice, they show like vibrations by the heat, okay? At high temperature, this vibration is quite high. On the other hand, this vibration becomes much more smaller at low temperature side. When the electrons, they passes through the lattice, this vibration can prevent the electron to pass through the lattice. So this is a resistivity. If you image to pass through the like a very congested place, you cannot easy to go ahead. The completely same image. So if the lattice are vibrating very strongly at high temperatures, resistivity becomes higher. So then when the temperature goes down, this vibration lattice becomes smaller, then electron can pass through very easy. That means the resistivity becomes lower. This is a low temperature image. Vibration becomes smaller, so an electron can pass through it very easy. If so, if we decrease the temperature as much as possible, just like near 0 Kelvin, how is the resistivity? So that was the top physics that nobody could answer around 100 years ago. Then one professor tried to answer to this question. He is a Professor Kamarin Onnes. So he was a Nobel winner in 1913. So what he did is, unfortunately, he was not a physicist. He was an engineer to start to create the liquid helium. So he was the first people to create the liquid helium. Then try to understand what is the resistivity at low temperature. So what he did is, he made this machine. This one is the original machine of the liquid helium liquefier, the first liquefier on the Earth. So he liquefied the gas helium into the liquid condition, and then cool down the samples down to 4.2 Kelvin. So this one is very completely handmade around 100 years ago, but this machine succeeded to get a liquid helium. Then he succeeded to measure the resistivity down to 4.2 Kelvin. But nowadays, this system becomes much more the upper class. Then what he found is just like a superconducting state. So what he measured in the beginning is mercury. The reason why he chose mercury is mercury was only the metal which is in the liquid state at room temperature. So then everybody was wondering how was the resistivity at low temperature side in such like a liquid metal. Then he found superconductivity. So the resistivity becomes nearly zero. So he couldn't believe this result, even though he measured this result. So then he named superconductivity. That means the resistivity becomes very, very smaller, like a 2 order, 3 order, 5 order smaller than the normal, the resistivity, usual resistivity. Then they couldn't believe the zero resistivity because the resistivity has to be happening around just 0 Kelvin. So he couldn't believe. Then he named superconductivity. So this is the beginning of the history of superconductivity in the world. Then this was the first observation. Then he's got the Nobel Prize in 1913. So that means zero resistance. Nowadays, we can understand that zero resistance. But Kamarin Onnes didn't believe that zero resistance. But we know now the complete zero resistance. Okay, so he's got the Nobel Prize. So after that, this was the successor, the 100 years later, this was a professor, they succeeded his Kamarin Onnes laboratory. So he showed some sort of, like, how can I say, lighting on the wall. This wall was moved from the one laboratory in the university, then they are displayed in a museum. So what is this is, after Kamarin Onnes found liquid helium, then has got the superconductivity, many the famous professors from the world visited his laboratory to discuss with Kamarin Onnes and to see the superconducting state. So then, of course, there you can know about the, you can see some sort of the very famous professor. For instance, here is the Max Born. The Max Born is also the very famous Russians. And if you see carefully this wall, you can find out the name of Einstein. So I found, when I visited there, of course, I saw the Max Born and Einstein's and many the famous professors whose name we can see in the textbook. So this was the beginning of the story of the superconducting state. Then after that, nowadays, this is the liquefier of the liquid helium. Now, for instance, in Japan, it's not so difficult to get the liquid helium. Then I'm also using my liquid helium in my laboratory. So only 100 years, they can develop the many technical viewpoint, technical things, and then we can easily use those kind of the cryogens, and we can go ahead. They're much more the top physics. So then, what is how we can use a superconductor? That is not so easy at this moment. So niobium titanium, niobium-3 titanium. This is just like a commercial-based the superconducting wire, which are being used for real productions. The typical production is linear motor car. So left-hand side is the Japanese linear motor car. Now this motor car can get 500 kilometers per hour nowadays. So then the Japanese government is now planning to open the linear motor car between Osaka and Tokyo in the 20 years. The right-hand side is moving, using the linear motor car, which is connecting from Shanghai airport to the city center, but this is only for 30 kilometers. And top speed is less than 400 kilometers at this moment. But this niobium-3 titanium wire is being used to move these kind of linear motor cars. But the superconducting transfer temperature of the niobium-3 titanium is like a 23 Kelvin. So in order to get a superconducting state, by using this wire, we still need the liquid helium, which is very expensive. So to liquefy liquid helium is still expensive, even in Japan, even on the world, even in any cases on the world, on the earth. So then they are better to use a much more cheaper cryogen to get a superconducting state. So how we can do is we have to increase the transfer temperature, even about the much more higher temperature side. So what is the criterion is, what the criterion is nitrogen. Nitrogen, the liquid nitrogen have 77 Kelvin. So if we can have the higher TC than 77 Kelvin, we can use the nitrogen as a very cheaper the cryogen, then making a breakthrough in the economic world. Okay, so this is just a simple image of the superconducting state. Why the superconducting state shows zero resistivity? Okay, zero resistivity means electron has no resistivity, no the barrier to pass through the crystal. So this is just like an image. Okay, when electron it comes into the material, some materials have the very strong interaction between electron and the lattice. Lattice means the atom. Then electron they would like to attract the lattice to the electron side. That means pull up, pull to the electron side like this. Then this shift of the atomic position is just like a deformation of the lattice. That means the vibration of the phonon. We say this is a phonon interaction, phonon-electron interaction. So then when the phonon, they appear just like when the lattice is deformed by the electron, then if another electron is near here, what's happened is when this deformed, the lattice goes back to like that, this deformed the lattice can attract the second electron to near to the first electron. So from the outside, these two electrons seems to be connecting each other, just interacting each other. That means one electron can pull up the second electron and forming the two electron state. So this means we say Cooper pair. So Cooper pair, they are just like one electron is passing through, pulling up the second electron. The second electron seems not to be seeing any barrier from the lattice. So the Cooper pair doesn't have any resistivity anymore. This is a superconducting state. So then what is the origin of a superconducting state is a formation of this Cooper pair. The important point is how this Cooper pair is formed. That is the key word to discuss a superconducting state. But this is a completely fast model to discuss a superconducting state by the Bardeen, Cooper, and Schrieffer. Then we say BCS theory. The BCS theory, the Bardeen, Cooper, and Schrieffer, they've got a Nobel Prize on the basis of this BCS theory. But nowadays, we understand this is a very simple, very fast stage superconducting coupling state. So then after 100 years, what happened? The two acids. In 1911, the Kammering Onnes has got the superconducting state on the mercury. But after that, lead, niobium carbonate, niobium nitrate, niobium germanate, then the TC becomes up to 23 Kelvin, but still the little bit higher than liquid 4 helium temperature, but below the liquid nitrogen temperature. So very recently, what's happened to us is, so the potential temperature becomes drastically higher than the liquid nitrogen temperature with say high TC superconducting cuprates. So the Bedroots and Mueller, they found the cuprate that is ceramic, lanthanum barium to copper oxide is ceramic. So they found the higher the transfer temperature, then now the record of the transfer temperature is 135 Kelvin in the world. So now the transfer temperature is higher than liquid nitrogen. So then we can think about the application of these materials as industrial devices. So for then what the big difference is between the normal, the superconducting state and also high TC superconducting state is high TC superconducting materials is a ceramic. It's not a metal, ceramic, just like a concrete. And also the ceramic shows the superconducting state. This is very shocking, the data. And also the usual superconductor, they forms the Cooper pair by using a phonon, but a high TC cuprate using magnetic interaction. So then nowadays, the magnetic interaction is a key to discuss how to increase the transfer temperature. For instance, this one is just like a demonstration how we can use the high TC cuprates. Okay, the usual metallic superconductor, we need to use a liquid helium, which is very, very expensive. But nowadays, by using a high TC cuprate, we can use the liquid nitrogen to cool down the high TC. So this one, the black part, this is just like a demonstration video, which was released around 20 years ago in the Japanese TV. So the black part is a high TC superconducting oxide, which has the higher TC than 90 Kelvin, that is much higher than liquid nitrogen temperature. So they cool down this high TC and put the magnet on. This is a magnetic floating effect. Please see the magnet is completely floating from the high TC. That means the high TC material, they push up the magnet. This is how to run the linear motor car. The linear motor car is using a completely same behavior. Okay. The one more interesting video I have, then I show you now. That is another superconducting effect, we say fishing effect. Okay, this one is demonstrated by the laboratory in Japan. So this magnet, we have the magnet here like that. So then this is high TC. The high TC at the room temperature, high TC just like a ceramic. It's not a superconductor. It's not a magnet. But if we cool down this high TC the cuprate by using liquid nitrogen, this liquid nitrogen, and also this cup is just like a cup noodle. Cup noodle, we put the high TC in the cup noodle and cool down by using liquid nitrogen. Then the samples becomes the superconducting state. Then if we put on the magnet, just underneath, okay? Underneath. So it's not connected, but high TC oxide can fish the material like that. So this is a fishing effect. So then they're rotating the magnet. So this was one of the interesting effect. This magnet is completely separated from the cup noodle, the cup. Okay, this one is how we can see the superconducting state. Okay, let's come back to the high TC, the superconducting state. So then what is the typical property of the high TC superconductor is this its structure. This is the typical structures of the high TC cuprates. This seems to be like a low dimensional structure. It's like a blocking layer and inserted by the copper auto plane layer. Then this is a basic mechanism. So the supercurrent in the superconducting state is passing through this coupled planes. This is a common property of all of the high TC cuprates. Then this is last one to couple hole. This is the first material to find the high TC superconducting property. And this one phase diagram of the last one to couple hole. So basically, can you see my video? It's okay. So basically, the high TC is basically the motor insulator because this is ceramic. It's a magnet. So then we have to dope the carriers as electrons are holes. Then we can see the superconducting state, killing the magnetic state. So then the carrier doping creates the superconducting state like that. So then the original state is the magnet. So then what is the important point is how we can understand this sort of magnetic spins inside the material. What is the static and dynamic properties of the magnet inside the high TC superconductor is very, very important at this moment. So this is now top physics of superconducting state, even at this moment. So and there are lots of research, many researchers in the world are studying how this magnet is behaving in the material. So then that is just a simple story and introduction of superconducting state. So if you're interested in, please think about some possibility to join to us. I've been to the Surakarta solo once and discussed with some researchers. And I'm now in Japan. So Japan, there's some sort of the offers to invite some of you to Japan to study with us only at the frontier of the top physics. So please think about it. And if you are interested in, please contact to us. Okay, thank you very much.
Okay, thank you very much, Professor Watanabe, for wonderful presentations. Okay, ladies and gentlemen, so the first talks we have already hear from Sparmi, and the second talks it is delivered by Professor Isa Watanabe. And Professor Watanabe have explained very clearly about superconductivity, yeah, and he already discuss, explain, and how the superconductivity material developed from the early step to the current nowadays, yeah, current. Okay, now we have 20 minutes for discussion, and I will allow you okay. We'll have 20 minutes for answer and question and answer. And so please just write your questions in your message underneath this screen, or you can direct your questions to Prof. Parmi or Dr. Isao. Okay, please, is there any question? Just mention your names from your institutions and to whom that question addressed to. Okay. Is there any questions? Okay. Once from Ahmad's side, yeah, this question is delivered to Professor Watanabe. I have one question for Mr. Isao. How can it rotate when high TC material reach superconducting phase, as shown in the video? Okay, that's your question, Professor Isao Watanabe.
The rotate means how we can switch the state to be in the superconducting state. Is it okay?
Yeah.
So actually, just simply to cool down. Simply cool down the sample. That is the only way to reach to the superconducting state. So then, in order to get the superconducting state, we need a cryogen, like a helium or nitrogen. Otherwise, we cannot see any the superconducting state. So that is the question. Okay. So then what is the ultra super, the topics is how we can have the superconducting state at room temperature. That is the dream of our physicists. Okay.
So otherwise we have to frozen the lattice. Is that correct, Prof. Isao? So
sorry.
We have to frozen the atoms so that the atom cannot vibrate, so the electron can pass through that space between two atoms. Is it like that?
It's not so easy to clearly say yes or no, because not all materials show the superconducting state at this moment.
Yeah. Okay.
But if you apply the very special conditions, some people said any materials show the superconducting state. That is a question about this moment. They're also the one of the general top physics. Okay. For instance, very recent information is just oxygen shows the superconducting state in the high pressure. So that is also very interesting property that was found in Japan. And also any metal like iron or something could show the superconducting state in the extreme conditions. So how we can generate the superconducting state, that is also the one question. Okay.
Okay, thank you very much, Prof. Watanabe. There is one more question for you. How is from Professor Budi Purnama? How do we explain the mechanism of current flowing in the superconducting material? So the second question.
Current flowing is we need to apply the voltage, of course. Otherwise, the current doesn't flow. So the current flowing, we can confirm that the current flowing by applying the voltage, just like to measure the resistivity. But unfortunately, in the superconducting state, resistivity is nearly zero. That is only the difference. So then the current flowing itself is the same with the normal metal. But the problem is the difference is in the case of the superconducting state, two electrons are pairing. in the metal, just only one electron is flowing. But in the superconducting state, one pair of the two electrons is flowing. That is the difference. But the flowing mechanism is the same. We apply the voltage and the electron is moving, following the voltage difference. Is it okay to your question?
Is that okay, Professor Budi Purnama?
Yes, okay.
Okay, that's okay, Professor. Is there any questions? Okay, there is another question. One question also for Dr. Isao Watanabe. Whether superconducting material application can be used for spacecraft application. So
at this moment, it's not realistic at this moment because we need to make engine for the aircraft. So then there was a sort of like a dream story how to flow up the aircraft, but this moment it's completely the dream. So for maybe in the next 100 years, I guess it's not so easy to realize such the applications.
Okay, is that okay, Dr. Ahmad Fauzi? Yeah, there is another question, I think. Greeting Dr. Isao Watanabe. I'm Zalia Satya from University of Indonesia. I'd like to ask something regarding the copper pair. Is it only viable on certain kind of salt lattice? And I'm kind of curious of the use of barium in its salt. What kind of property does it give to the whole system as a superconductor? Thanks.
At this moment, there is no clear rule what sort of things become superconductor or not. There is no clear rule at this moment. We have to see one by one.
Okay,
For instance, the organic salts. Some organic salts can show the superconducting state, and metals and ceramics and some sort of the semiconductors also show the superconducting states. At this moment, in order to find out the superconducting materials, that is just like something like trial and errors. So even though your sample doesn't show the superconducting state at low temperatures, that cannot guarantee whether your sample is definitely not superconductor or not superconductor. So then, if you want to make a superconducting state in the sample, they check the low temperature property. So then the next one is try the extreme conditions, just like a super high pressure or something. So high pressure could change the electric state from the normal metal to be a superconductor. That is a general tendency at this moment. That is why the oxygen can show the superconducting state. So check first the resistivity at low temperature, then think about. Is it okay?
Okay. Is it okay, Dr. Azela Satya? I think it's okay, Prof. Okay. There is another question, I think. Okay. So then in conclusion, it's a trial and error. Oh yeah, jadi Mr. Satya just try to make conclusion. So is it right that to know that whether the material is can have superconducting property or not is by trial and error? Is that correct?
Yes, it's correct. So if you're interested in a superconducting state, then if you are in the Universitas in Indonesia, please visit Professor Budi Kurniawan. He's my collaborator, and I'm now deeply collaborating with him. So then I've got some students from UI. So then if you're interested in a superconducting state, just please visit his laboratory. Maybe he could show something interesting to you.
Okay, thank you very much, Professor Isao Watanabe. Is there any more questions? Okay, I have one question for Professor Suparmi. Professor Suparmi, you have a questions from the your last presentation. That's absorption coefficient is called absorption coefficient 1 and plus absorption coefficient 3. Yeah. So what is the contribution of the absorption coefficient 3? Is it to increase the absorption coefficient or to decrease absorption coefficient?
Oh, okay, Pak Marzuki. This new material, the quantization energy at subband, because there is interaction between electromagnetic and the material. That's why there is a absorption, the first degree, second degree, or third degree, also determined from the matrix of the density operator of the electron. So depend on the, what is it, frequency of the electromagnetic that is interact on the material. And actually, because I did not really learn a lot, and I hope this material, this investigation, maybe I will work with you with your project, maybe. Yeah, and this is I just started, so, and I did not learn a lot, so maybe me and you will talk later about that. Yeah, and maybe our project, what the recent project, we had some big fun, I think. So maybe on this theoretical calculation later, we will explore some potential, and then the result of the determination of the optical absorption will be compared to the absorption that the material that you fabricate. Yeah, maybe, and then we'll choose the potential that is the most agreement with the experiment.
Okay, that's great, Prof. I will be very happy.
So you will learn it.
Yes, of course, Prof. I will learn it, Prof.
Yeah.
I will study hard for maybe to understand that.
Yeah.
Thank you very much, Prof. Thank you very much.
Yeah, you welcome.
Okay, is there any more questions, ladies and gentlemen? Okay, if not, I think that is the end of the second sessions of this conference. And ladies and gentlemen, if you have maybe any more questions, yeah, after the end of this conference, this discussion, you can maybe send a message to both Prof. Suparmi or Dr. Isao Watanabe. Is that correct, Prof. Suparmi? And is that okay? And Dr. Isao Watanabe? And I think I will not make conclusions. And on behalf of the conference committee, we thank you very much for these great talks, both delivered by Prof. Suparmi and Dr. Isao Watanabe. Okay, thank you very much, Professor Suparmi, and thank you very much, Dr. Isao Watanabe. And now time back to the MC.
Thank you, Dr. Ahmad Marzuki, for being the moderator for the second session of the plenary lecture. Ladies and gentlemen, we are now at the end of the plenary lecture session. The next on schedule will be the parallel session. The breakout room will be open at 12:45 p.m. and the parallel session will start at 1 p.m. Here are the rules for the parallel session. Please join the Zoom 15 minutes before the event start. Each presenter must be in the virtual room throughout the session. One presentation is allocated 12 minutes, with 7 minutes for the presentation and 5 minutes for the question and answer session. Presenters have to close the presentation strictly within 7 minutes. Session chairs need to strictly control the start and closing times of each session. During your presentation, the session chair will give you a notification via Zoom chat 2 times, indicating that your time is coming to an end. The first notification, 3 minutes time remaining, and then second notification, the time is over. The question and answer session. Participant can give the question through chat that will be read by the chair or directly unmute your microphone, but ask the permission of the chair first. If there is some trouble with the connection or the technical from the presenters, it will be skipped and will be continued by the next presenter. The skipped presenter can present the manuscript at the end of each session of each room. Once again, we give many thanks to all of our wonderful keynote speakers today. We thank every committee member and also the participant for the wonderful accommodation. I am, as the host of this conference, will sign off. Thank you and see you in the International Conference on Science and Applied Science 2022. Wassalamualaikum warahmatullahi wabarakatuh.